Hello, I'm Frank Ferdinandi of Azurian Technology, and I have been invited to give a presentation on a novel surface finish that has significant environmental benefits. I have put together a set of slides that show some of the results from testing the first generation of this coating, but before I go through them, I will explain my interest in surface finishes and where the idea for this new surface finish came from. My background is a combination of electronic hardware design and electronic manufacturing. I started designing products after I graduated in 1972, with my first design using surface mount technology coming in the mid-80s, when I was working at the technology division of PA Consulting. I became involved in a prototype surface mount assembly facility that was set up at PA to prove out designs before transferring to a client for production. In 1988, I and a colleague spun this out to set up a contract electronic manufacturing company. After 6 years of being involved with that company, I went back to PA and resumed my career developing products. But now I also got involved in manufacturing assignments. I spent 12 months at Panasonic doing performance improvement, including sorting out one of their soldering lines. I worked as an interim manufacturing manager for a supercomputer company. And I worked on a project for Philips Lighting where I was the liaison between the manufacturing plant in Holland and the design team at PA. I also liaised with the Philips Advanced Manufacturing Centre. I encountered a lot of problems with surface finish over the years, both as a hardware designer and as a manufacturer. I had a couple of problems with OSP at Panasonic. I encountered tarnishing with immersion silver, and with ENIG I had problems with Blackfoot. Also, when I was designing a product with a Motorola Power PC, the application note advised against using ENIG for prototypes because of the difficulty of getting reliable joints after replacing components on prototype boards. In 2004, I was invited into a brainstorm at PA by a colleague who specialised in plasma polymerisation. The brief for this brainstorm was to find other applications for an ultra-thin PTFE type coating that was being used for waterproofing clothing. My first suggestion was, if it can be used for waterproofing clothing, why not waterproofing electronics? At least 2 companies are currently coating millions of phones a year based on that suggestion. I then asked if I could solder through this coating. The response that I got was, "Don't be daft, everybody knows you can't solder through PTFE." But my interest was piqued, and so after the brainstorm, I got hold of several circuit panels that had been rejected after etching, and I persuaded my colleague to get them coated. When they came back from coating, I took one to our lab and got out a soldering iron and a reel of multi-core solder. When I tried to solder to the copper, it just flowed. So I tried several other areas and they all soldered very easily. To test the strength of the joints, I took a leaded resistor and soldered one lead to the copper, and when I tried to pull the resistor off, it would not budge, so I knew I had a good joint. I walked up to my colleague, who had got the coating done, swinging this panel by the resistor, and asked him to explain it. This was the start of a whole series of testing that was initially carried out in my spare time and then followed by an internal project with departmental funding, after which the venture capital arm of PA took over funding and a company was set up to commercialise this surface finish. The first few slides that you will see come from the introduction of a presentation that I gave to the PA board when they were considering putting this with the venture capital company. Now, one of the interesting things that I'd like to point out about this slide is that the bead of liquid that you can see sitting on that circuit board is actually highly concentrated nitric acid. It will sit there for about 20-25 seconds, long enough to get a photograph, before it actually starts to burn through the coating and attack the copper underneath. But to get this photograph, you have to have the board sitting perfectly level. The slightest tilt on it and that acid will just run straight off without affecting the board. The shelf life provided by this coating is illustrated in the top right hand photograph. That panel had sat under my desk just wrapped up in cardboard for 4 years and it was still oxidation free. I still have that panel 10 years on, and yes, it is starting to oxidize now, but I can still get good solder joints to it. My initial way of testing the strength of the solder joints was to solder the SO devices and then get a small electrical screwdriver and stick it under the end of the device and try to prise it off the board. In all instances, either the solder pads ripped away from the FR4 or the device broke. There were no incidents of the solder joint itself actually pulling apart. I tried a number of different reflow ovens when I was doing the soldering. I tried vapor phase and wave soldering, and it worked with both lead-free and leaded solder. One of the benefits of this coating is that whilst the coating is removed from the point of soldering, it leaves the rest of the board with a coating that provides a high level of protection in aggressive environments, so you can get longer product lives. And also there are no rework issues with this. It's very easy to rework. This coating has significant environmental benefits. There's no water required and any waste is eliminated. And the materials are far more environmentally friendly. There's no need for cyanide, there's no need for thiourea, and we can eliminate nickel as well. The photograph that you see on this slide is of a forest near to a nickel processing plant, I think in Russia. And the forest has been totally killed by acid rain from the processing plant. This photograph shows a typical plasma chamber for the coating. They come in a variety of sizes according to the requirements. This particular one has 5 shelves in it to allow for multiple stacking of PCBs. It can also be engineered as a fast, high throughput system by fitting doors to both sides of the chamber and using semi-automated loading. One of the other features of this is that you can actually do in-situ cleaning of circuit boards, although this does have some limitations. So now we move on to some of the results that we got from the soldering program. You can see the typical joints for an SO20. We had joints sectioned so that you can see that there are no voids in it. You often get some voids, but no significant voids here. And it also shows that the coating has disappeared altogether where the solder's been. Tried soldering vias and got quite good results from that, and you can see the intermetallics of the via. I managed to solder vias at 0.2 millimeter and got the solder right up to the top. It's not quite over the top. I couldn't manage to get it to put a fillet on the top, but it came pretty close and certainly met the IPC 610 standards. There's a better view of the joint where you can see the intermetallics, which are quite clean and quite good. Tried fine pitch and again got very good joints. BGAs, no problem at all. Went down to 0.8 millimeter BGAs, but again we had them sectioned and you could see the intermetallics there that are quite good. I decided at this point that I needed independent verification of some of the results that we were getting. So I went to the National Physics Laboratory in London for them to carry out shear strength tests on the solder joints. And you can see some of the equipment that they used for that. We achieved excellent solder strength results with low standard deviation. We used an NEPIG board as a reference and an OSP board as well. We also got them to carry out preliminary aging trials where they stored the boards for 150 degrees C for 10 days, which is equivalent to 10 years. The joints on our board reduced by about 15% in strength on average, as opposed to 25 to 30% for the NEPIG boards. I then had wetting balance testing done by ST&S in the US, and they came up with these results, which were quite good. So I then went on to look at electrical properties. So what we had achieved so far gave us an equivalent of a super OSP, if you like. But for some reason, which I still don't know why, I got an electrical milliohm meter out and started trying to measure the electrical resistance of the coating. Now, we measured initially a resistance of 0.1 ohms, or less than 0.1, but I wasn't sure whether I was just pushing through the coating or what was happening. So I then got a number of boards coated with different thicknesses, and again measured the resistance, taking care not to push through the coating, and I was able to plot a linear relationship between the resistance and the thickness. This convinced me that it was actually a property of the coating and not a push through of the coating. I then decided to have the surface insulation resistance measured, because I was concerned that given the low resistivity that I'd encountered in the Z-axis, I was concerned that there might be low resistivity also in the X and Y plane. So I went to MPL and got them to carry out a series of SIR tests, and you can see the results here. Our coating is not as good as ENIG, not even as good as OSP, but still above the minimum industry standard acceptance level. Because PTFE is used as a dielectric in a number of products, I decided to find out what the high frequency performance of this coating would look like. So a colleague at PA designed a number of strip lines so that we could measure the impedances at frequencies typically used by the mobile phone industry. So around about 600 megahertz, 1 gig and 2 gigs. And what you can see from these measurements is that the selectivity of our coating with two different thicknesses of coating and OSP compared very well across all three frequency bands. But the ENIG and NEPIG coatings, all the selectivity dropped off as the frequency went up quite significantly. So you can see significant benefits for this coating at high frequencies. My next challenge was, well, can you wire bond through it? So I went off to a company that specialised in wire bonding and worked with them on a couple of visits. And we were able to achieve very good wedge bonding results for both aluminium and gold wire. And we got to a point where the wire was breaking before the bond in all the tests. I tried ball bonding, but that was a no-go. I suspect because of the coefficient of friction of the coating. We then started a series of corrosion tests on the coating. The first one was a 24-hour test with gas phase sulfur dioxide, where we left an azurin board and a NEPIG reference board in a chamber with a high sulfurous acid content at high relative humidity for 25 degrees C, and you can see the results after that 24 hours. The coated board is showing no signs of corrosion, whereas the NEPIG reference board is unsolderable. We then carried out another sulfur dioxide corrosion test, where we then changed the environment to a sodium sulfite solution. Left that for 24 hours, high humidity, and at a raised temperature of 41.5 degrees. Again, after the test was completed, you can see that the coated board has no signs of any blemishes on it, whereas the NEPIG board is totally destroyed as far as soldering is concerned. In the two 24-hour tests that we carried out, the chamber was given an initial charge of the corrosive gas and not replenished during the test. The University of Limerick had developed a mixed flowing gas test in conjunction with the IPC 311G Surface Finish Committee, where the corrosive gases are constantly replenished during the test. The mix of gas used is representative of a polluted environment that might be encountered in somewhere like Mumbai. 1 day in their chamber represents 1 year in a Mumbai environment. This slide shows the results of the tests compared to ENIG, OSP and immersion silver. The immersion silver and OSP boards were both basically unsolderable after 1 day. The ENIG board managed to last for 3 days, whereas ours was still going strong at 20 days. This test is based on the Battelle specification for the environment in Mumbai. This is our first stab at comparing our coating to other surface finishes. Obviously, it's highly subjective and I'm biased. Thanks for your time. Frank Ferdinandi.